Hello everyone and welcome to a new discussion which we are going to have today on field determination of transmissibility and storage coefficient. And this discussion I have kept in two parts, otherwise this becomes very lengthy. If you recall our previous discussions which we have done using different equations or methods given by Thyme, Thais, Jacobs about the same about determination of hydraulic characteristics of aquifers. Here also we will be using field determination methods for transmissibility and storage coefficient determination. So, let us start with this that the major in groundwater studies, it is always to know that whatever the aquifers which we will be tapping for groundwater supply or for irrigation or drinking or whatever, then the aquifer should provide water as and when we want. That means it should provide water perennially. We should be able to withdraw water all the time. Whether it would be possible or not, that is a different story. But the target or objective of groundwater studies is to determine how much water can be withdrawn from any aquifer on regular basis. So, to achieve this kind of objectives, we need to know the transmissibility and storage coefficient of aquifers. Second is we need also the lateral extent of each aquifer and the hydraulic nature of its boundaries. Always remember that we are talking about subsurface invisible geologic formations or aquifers which do not have any manifestation of their presence and characteristics on the surface. And therefore, in subsurface condition we must know what is the lateral extent in horizontal directions, in all horizontal direction, what is that lateral extent, and also the hydraulic nature of its boundaries. Because aquifer boundaries we have already discussed, and there can be various types of aquifer boundaries. So, we must know wherever we are going to tap the water and expecting that we would be able to withdraw water perennially or on regular basis, then these things are required. After transmissibility and storage coefficient of aquifers, then lateral extent of aquifers and boundary, hydraulic nature of its boundaries. Also the vertical position of aquifer, how they are aligned or positioned in a section or in vertically, and again the hydraulic characteristics of overlaying and underlaying beds, because we may be having confining aquifer conditions. So, we must know about those characteristics, that means hydraulic characteristics of these two beds and of course the aquifer. So, not only we are trying to find out the hydraulic characteristics or transmissibility and storage coefficient of aquifers, but also we need to know the top part, what is the top rocks and what are the bottom rocks of that particular aquifer. And finally, the effect of proposed developments on recharge and discharge conditions, because we have said that we would like to withdraw water perennially, but what is the possibilities of getting water recharge, or from where the water gets discharged and can come in our aquifer. So, all these informations are required and which can be required through field determinations of this kind. Now, this first we will go one by one. So, the transmissibility and storage coefficient of aquifers. So, there are different methods to determine the transmissibility of an aquifer, and the most commonly used methods are: number one is the laboratory test of aquifer samples, if we are having, because many times getting subsurface samples is a challenging, and the reason is because when drilling is done, the large pieces may not come out if the borehole size is not very big. But anyway, if rocks are available or lithologs are available about the vertical positions of different geologic formations, then those tests can be performed. Secondly, the regional analysis of water level maps. This becomes very important for any kind of groundwater related field investigations. We not only we are interested to withdraw water perennially from any particular aquifer, but for that we should know what is the regional water level and how rocks are varying. At least that information, the surface information would be available on maps. And geologically it is possible sometimes to create the geological cross sections, and can the subsurface condition can also be understood to large extent. So, this geological maps or regional analysis of water level maps can give a lot of insights about the about to achieve our targets, and that in our first example is transmissibility and storage coefficient. And the other important thing which we would like to perform once these above two methods have been done is the aquifer test, or also called pumping test. This is a very common and a very reliable method of field determination of transmissibility and storage coefficient. So, we will discuss in detail about the aquifer test and pumping test, which involves the withdrawal of water from or addition of water to an aquifer. And theoretically we can always think in that this reverse drawdown curve can also be thought if we add the water, but practically it becomes very difficult. So, the first part, how to test a aquifer or a well, is withdrawal of water for long time. And earlier also in previous discussion, like in Jakob or Thais methods, we have also discussed that the water should be withdrawn for longer time to get the steady state condition. So, the change of water level in aquifer is observed through a well or observation well and analyzed using several different equations, as we have already discussed in our previous discussions. So, these water levels are then observed, monitored, and then analyzed at the same time. That means same times means whatever the water level I am getting in the well which is being analyzed and in surroundings. At least two wells should be there, and if they are in one line, then it would be much better situation. Now, in this but we must know when we are performing this aquifer test or pumping test, that change in water level is dependent on various factors. Which are those factors? Number one is the type of well used to withdraw or add the water. Adding water is, I have already mentioned that in rare conditions it is done. Withdrawal of water is much easier in that sense, if water is available. If water is not available, still we want to perform the aquifer test or pumping test, then adding the water can be done. And rate at which the water is withdrawn or added. So, this we will also, this factor will, the water level will depend on this, that at what rate, how the pumping is being done. So, how the water is getting withdrawn from the well or added, and the length of time of the pumping test. And during these pumping tests, the length of time may be, depending on the aquifer conditions, maybe 24 hours or more, so that we get a steady state conditions, if we are getting at all. And then hydraulic characteristics of the aquifer, that is basically our aim, but water level depends on all these factors. And also position and nature of aquifer boundaries, because aquifer boundaries plays very important role. We have already discussed few times that aquifers are neither isotropic nor homogeneous, and they do not have infinite extent either, horizontal or lateral infinite extent. So, therefore, these aquifer boundaries becomes very important factors which are controlling the change in water level. So, now we will discuss different conditions, and the first one which we are going to discuss is non-steady state and steady state conditions. In our earlier discussions, we have discussed mainly the steady state shape and steady state conditions. Now, we are going to discuss, which is most common, is the non-steady state. So, how in non-steady state, if we do not achieve after pumping of 24 hours or 48 hours, if we do not achieve steady state or steady state shape or steady state conditions, then how we can determine the transmissibility and storage coefficient. So, in such non-steady state conditions, how things can be performed, that we will see now. So, as we know that when water is being withdrawn from a well, water in the vicinity of the well will go down, water level, and there will be development of a drawdown, and that will, as we have also seen in our previous discussions, that would be an inverted cone and whose apex is at the center of the well. So, here drawdown is also, or we also call a cone of depression. So, the drawdown is happening like this. So, initially the water level or depth to water level was here, and now this is a unconfined aquifer conditions. Water is being withdrawn. So, slowly this after pumping for some time, the water level may reach to this. So, this we consider as drawdown, and a radius of influence, that means the radius of that cone of depression or the base part, if I say base part of the cone of depression is this radius of influence. So, that will give us the idea about the cone of depression. So, all these observations are required in non-steady state conditions, so that we can determine the transmissibility and storage coefficient or storageability. So, initially when we start pumping water from a well which being under observation, the water is removed from the storage in the aquifer materials which are the close to the well, and the water withdrawal may be little higher, relatively rapid rate, because the water for the pump is available in nearby places, and therefore, the output may be high. But later on this because the water has to come laterally from all directions towards the well, and therefore, the output may reduce. So, this these conditions gradually this cone of depression, and this cone of depression may become something like this, may develop like this, as shown through 4 or 5 bands of colors, different colors, that initially the water level might be this, or cone of depression might be this, then the cone of depression can become like this, and later on. So, it will laterally it will expand, and not only laterally, but vertically it will also expand if we keep withdrawing water from the well. So, generally the cone of depression expands to encompass a larger and larger water supply area, and the rate of decline of water levels diminishes. So, because you have to think that at initial stage the lateral extent is less. So, the water which is available nearby places will be withdrawn initially, but later on when we go deeper, then our lateral extent increases, and that is why the decline of water level can diminish after some time. That means that the output from such wells, if we keep withdrawing water, will become constant, and that is what generally we say steady state conditions, but may not be such there in all aquifer conditions. Now, the water level which is approaching the stability in certain hydrologic situations or in certain geological conditions, if the water continues for long enough, and in this example this see it is started from 1 year, then 5 year, then 10 year, and then 20 years. So, you know, for a long time, this is what the long time means here, but not continuously pumping is been done, but the cone of depression may become larger, lateral extent may be larger, the base of the cone can occupy a very large area. Now, there may be in such situations there may be 2 different conditions. The first one is the non-steady state conditions. The non-steady state condition here is that when the rate of flow through the aquifer is changing, not getting steady state, and water levels are declining, and that condition we call as non-steady state condition. Because the non-steady shape, that means the cone of depression shape is also not getting stabilized. So, this is a condition where this the withdrawal of water is keep changing. Initially in all such experiment the non-steady state is there, but in some certain aquifers we can achieve steady state also. But if this the withdrawal from an aquifer keep changing, and water levels are declining, then we call as non-steady state. Whereas in a steady state conditions, when the flow is steady and water levels have ceased to decline, there we call as steady state. Everything is settled, you can think in that direction, that everything has settled. But in case of non-steady state, nothing is settled, your withdrawal rate is also changing, plus your level is water levels in the well are also declining. Further, there are two important points or changes which should be considered while analyzing or going for field determination of transmissibility and storage coefficient. And these are the what are the two main changes. First one is the water level and rate of flow. How the water is level is declining or being maintained in a well, and what is the rate of flow, how the water what is output of the water from a well, and what is the shape of the cone of depression. Because if water level is not changing and rate of flow is also not changing, then cone of depression will also become in a non-steady state shape. That means it will not change. So, if a cone of depression is changing, then other two might be also changing. So, that is why it is important here. Now, in a more aquifer which are directly hydrologically connected to perennial streams, now we are considering a aquifer boundary here, and aquifer boundary in our case is a discharge area. That means the groundwater is getting into the river itself. And so, what would be, and of course, this is the top part, we are taking example of unconfined aquifer condition. In the middle, we are having confined aquifer conditions, and also in the bottom we are having confined aquifer condition. And these two beds, one is confining and another one confining, they are making successive confined aquifers which are at lower levels than confined aquifers. So, in aquifer which is being tapped by the pumping well, initially the water pumped from well which is derived from storage is in the vicinity of a well. Whatever the water which is getting pumped here, initially in initial days the water will be coming to the well or out of well from nearby places. But as pumping goes on and no recharge is taking place, and then or sufficient recharge is not taking place, then this cone of depression will become larger and larger, and the areal extent will also increase. And this is what so initially it is the days, then it goes to the years. So, initially the water pumped from the well which is derived from storage in the vicinity of the well, and later then removal of water will form the cone of depression around the well, and this continues, and if we continue the pumping for some time, the central portion of cone assumes a relatively constant shape, and of course, first near the pumping well and then gradually to greater and greater distances. That means that the cone of depression starts getting steady shape, or water level gets a fixed position in a well initially, and then this gradually away from the well, this also stabilizes and gets the shape becomes steady shape, and this shape is determined by the hydraulic gradient needed to transmit water through the aquifer towards the pumping well. So, the water which will be coming from there, if we are still in unconfined aquifer conditions, but in confining aquifer conditions the things will be little different. But this well is not going through the confining beds. So, the effect of withdrawal of water in this particular example cannot be considered here. Anyway, so during this intermediate stage, after the first stage when the water is coming into the well from the very nearby places or surroundings, and then later on from little far places. So, the water level continues to decline throughout the cone of depression, and the rate also declines, which is very nearly uniform in the central portion. So, what basically here meaning is that the steady state conditions starts developing first near the well and later on at distances also. So, ultimately this cone of depression reaches the stream in this particular in unconfined aquifer conditions, it can reach to the stream, and in this example the stream is discharging, and to begin the groundwater discharge or reduces infiltration into the aquifer, and that may create some problems, but depends on how things are on the ground. So, in such situation or at that moment the water level begins to approach stability, and that means we are approaching towards the steady state condition. So, if this reduction in the discharge to the well or the infiltration equals the pumping rate, the decline in water level also ceases, and there will not be further decline in the water level in the well. And some of the equations which we have discussed or developed earlier for the determination of transmissibility and storability can be applied to all these three stages, and that means initial stage, middle stage or later stage in the development of cone of depression or understanding the cone of depression, or ultimately what we would like to know the transmissibility and storage coefficient. So, in this discussion or in later discussions, there are few terminologies which are important here to understand the equations of hydraulic characteristics of aquifers. So, which we have discussed steady state, non-steady state. Now, non-steady state and non-steady shape. First one is this one, the condition exists during the early stage of withdrawals, when the water level throughout the cone of depression is declining and the shape of the cone is changing or relatively rapid rate, and that is why it is this non-steady state is mentioned here for the level of water in the well, and non-steady shape is mentioned here for the shape of cone of depression. So, neither water level in the well and nor the shape of cone of depression in initial stages gets stabilized, and therefore, this terminology is used non-steady state and non-steady shape. Another condition can be that non-steady state, but steady shape. That means now the water level is in the well is declining, but overall the cone of depression has got stabilized. So, here the condition exists during the intermediate stage, and this was the early stage of withdrawal, non-steady state and non-steady shape. But here it is the intermediate stage when the water level in the well keeps declining, however, the cone of depression or the central part or cone of depression becomes constant, and therefore, we give this wordings to non-steady state, but steady shape for cone of depression. Now, in the last now we are coming to the third stage, which is completely steady state, and this condition exists in the final stage of withdrawal. For final stage means here for longer time, when the water is getting withdrawn for continuously for many days together, then we may call that stage or that condition as final stage, and there the water level will not drop in the well, and nor there will be any change in the cone of depression. So, that is a steady state in both cases, in water level case as well as in your this shape also of cone of depression. So, that means that the rate at which conditions in a aquifer proceed from non-steady shape to steady shape outward from the pumping well, which depends on several factors. So, initially all are non-steady or both are non-steady. In the middle stage one is still non-steady, but cone of depression becomes steady. In third stage or in final stage, all two becomes steady in a steady shape. Neither water level is declining, nor there is a change in cone of depression. Now, to proceed further from non-steady state to steady state outward from the pumping, which will depend on several factors. Which are those factors? The most important of which or these conditions is about the confining and confined aquifer conditions. So, these whether we will achieve steady state or not will depend on one of the important factors, that is the confining or unconfined aquifer conditions, which will affect everything here. And then finally, the steady shape conditions are approached more rapidly under confined aquifer conditions, because the aquifer is confined with two impervious layers, and therefore we can achieve quite relatively early the steady shape or steady state conditions for water level as well as cone of depression. Whereas in unconfined aquifer conditions, the smaller storage coefficient of artesian aquifers may also in that conditions may also achieve that steady state. Otherwise, in unconfined aquifer conditions, achieving a steady state condition becomes very challenging. So, in this part of this field determination in transmissibility and storage coefficient, we will stop here, and in next part we will see further about the aquifer test. So, thank you very much for time being.